Hi, this is Phil Koopman, and I'll be talking about software development processes. Let's start by taking a look at all the activities that go into creating software. There's creating system specs, otherwise known as requirements, conceptual high-level design, detailed design, running simulations, testing and debugging, prototyping, and sending to production. At the bottom of this chart is documentation, coding, and meetings, and it runs 1 to 2% of the entire effort to create software. What this is saying, at the risk of oversimplifying, is that coding is basically 0% of creating software. Looking at it another way, there's all these types of things you do to create software, and the code itself kind of comes out at the end. Now, to be clear, you can spend 99% of your time actually writing the code, but that's not the kind of software you really want to put into a mass-produced product. All those activities have to be organized somehow, and the way they're organized is called the software development process. Here's a picture of an old-school waterfall development cycle, and it's called a waterfall because things flow down from the top left down to the bottom right. First, they're specifying the product, which is product requirements. Then they're specifying the software requirements, creating a software architecture, which results in a high-level design, designing individual pieces, individual modules, which gives you a detailed design, implementing, that's the part where you actually write the code, and then taking the source code and doing testing and validation, and finally deploying and maintaining. The waterfall process is effective for well-understood domains. If you've designed 57 thermostats before, and you're making thermostat number 58, and you know what all the requirements are, and you have a good idea what design is going to work, waterfall might work very well for that. It works best if you do not make a lot of big mistakes. So for example, if you make a big mistake in the product requirements and don't find out about it until you're testing and validating, you have to go all the way back up the waterfall and back down it again to make the change. So changes can be very expensive, and this is optimized for projects on mature technology that know pretty much what they're going to do and how they're going to do it, and they just need to get all the pieces done. There's a myth out there that waterfall means you can never go back, but in fact, the original waterfall paper had these backward arrows for bugs. So it's not that you're not able to make changes, it's simply that going back to make changes is pretty expensive. In the 50 years or so since waterfall processes were the cutting edge of technology, we've learned an awful lot. Here's a summary of some of the lessons. A big one is that dividing a system up into the right subsystems is absolutely critical. If you have a bad architecture, your project is probably doomed. So figuring out of all the code how to slice it up into pieces that make sense and how to organize the pieces as they work together is absolutely essential to success. Making a big pile of spaghetti code and tossing it down the waterfall is not going to work for you. Another important lesson is that process formality is a good investment. It's awfully tempting to dive in and just write some code and skip all the traceability and the process steps in the formal reviews. Skipping steps costs more in the end. Emphasizing the importance of the upper left side of the waterfall, basically the beginning of things, requirements are important to get right, and unfortunately, requirements change. So that suggests using an iterated approach. The really big problem with a waterfall is even if you understand your requirements perfectly, if they change, you have to iterate back up the ladder, make a change, and then flow back down. It can be very expensive and very disruptive to have a late-stage requirements change. That having been said, people are really eager to start writing the code. In fact, sometimes they just skip requirements, figure out, well, this will be close, and they start writing some code. Usually you get a bad result from doing that. A good quote on this is, if the second half of the project is debugging, that must mean the first half is bugging. In other words, developers are eager to start writing code so they can get down to the debugging to try and get some of those bugs back out. Finding bugs early is important, but the best way to find bugs is to avoid the bugs getting in the code in the first place. So you do things like traceability from high to low levels. You make sure the code you write actually matches your requirements. You make sure you test code in small modules first before you do system tests. And you do peer reviews so that human eyes take a look at the design and the requirements and the software before you ever do testing. And finding bugs that way turns out to be way cheaper and way more effective than waiting until product test. It matters a lot whether you find bugs early or late. The later you find them, the more expensive it is. One way to look at this idea is the Swiss cheese model. So the idea here is there are a bunch of bugs in the software at the upper left, and there's a piece of Swiss cheese that if there's a hole there, then the bugs escape, they get through, and if there's no hole, they get caught. So that slice of Swiss cheese you're seeing is product test. And product testing will find some bugs, but not all bugs. The things that escape through the Swiss cheese are software failures that will happen in the field to your product. So product testing is important. It's late and it's expensive, but you do have to do it. You certainly need some way of doing one last check before you ship the product. But if that's all you do, you're going to have a lot of escapes, bugs escaping into the field. So what can you do in addition to product testing? Well, you do software testing. The difference is that product testing tests the product features like a user would use the system, where software digs a little deeper and is able to stress the software more thoroughly. For example, things that would be very unlikely to happen in the product but you have to handle, the software testing can get at a lot more easily. So software testing includes unit testing, integration testing, and software system testing. The idea here is that the holes will be in different places and it will be able to catch some bugs that product testing cannot. Now, some might still get through, so you need to do something beyond software testing. You can do code peer review. Code peer review involves people taking a look at the code and trying to find bugs. And it turns out that people doing that will find defects that are difficult to find in testing, but pretty obvious if you carefully look at the code. So the code peer reviews will find some other bugs that would have otherwise have escaped and made it through software testing, product testing, out into the field. Code peer review happens earlier in the process and is a lot cheaper than product testing. You can do something even before code peer review. You can do design peer review. Design peer review happens even earlier in the process. So design peer review is where you look at the software design, not the code, but the thing that comes before the code, and remove logic errors before the code is ever written. That's even earlier than code peer review and even cheaper in terms of cost to find defects per line of code than things like product testing. The idea with the Swiss cheese model is that if you have lots of different ways to find bugs that do it differently, it's much less likely, or you'll have far fewer defects escape into your fielded product. And that's what you want to see. If you're interested in what this looks like in practice, you really want to be finding half to 3/4 of the bugs up front. On a good day, you find at least half or 2/3 of the bugs just in design peer review and code peer review. Software testing finds most of the rest, and in really good software, product testing finds almost nothing. You should be finding most of the bugs up front. Product test should be the last check to make sure there's nothing there you didn't think of. This approach can make software less expensive and absolutely higher quality. Fast forward a few decades, and the V model has emerged as a common development cycle used in embedded systems. The V model adds two critical things that are missing from the waterfall. The first one is that it adds the idea of tying tests to different layers of design to be more effective finding defects earlier before product test. And the other is better support for decomposition so that if there are multiple teams working together on a product, it's easier for them to collaborate within the context of the software development cycle. The V is called the V model because it looks like a V, as we'll see. The first step in the V is to specify a product, and the output of that step is product requirements. So now you know what product you're trying to build. The next step is to specify software, and that puts out software requirements. Now you know the software's role in the product. The next step is to create a software architecture, and that results in a high-level design. So you've done the requirements, you know what you're building, and the architecture is the general way the components and functions will be organized to build it. After that comes designing the different software modules, so those are the pieces within the architecture, and each module ends up with a detailed design. Now it's time to implement, which means writing the code, and so you create source code. Now to this point, this looks an awful lot like the waterfall, and in fact, it's very much like a waterfall. The one nuance in there is that there's a presumption that the designing of modules might be done by different teams in parallel. And so as you go down the V, things break apart into pieces, and as we climb back up the V on the other side, they come together to integrate a system. Once you have the source code, in the waterfall it just says do test, and typically that ended up being system test. But the V is more nuanced about it. The V says, all right, after you have source code, we're going to do a thing called unit test. And unit test is going to take what was in the design of the modules and just make sure each module works without worrying about what other modules are doing. So each module design team can do its own unit tests in parallel, and you can test without waiting for the whole system to be done. The unit test results find some bugs, so it's another layer in the Swiss cheese model. And then you take the units, you assemble them into subsystems, and you look at how all the units play together. Basically, you assemble the units into the high-level design and make sure that the system conforms to the high-level design, that it works the way you thought it did, assuming the units are already taken care of because you've already done unit test. Finally, you integrate all the software into the whole software system. You do software test. And only then do you do acceptance test on the product. So the last thing you do is a product test, and that should just pass except for potential some weird hardware-software integration issues, because you've already thoroughly tested the software and you've done a methodical design. Now the piece that's missing are some arrows that go back and forth that explain how these things relate to each other. So for example, on the upper left, there's a specify the product, and that goes to the acceptance test. In other words, when you're done with a product spec, you create a test plan, and that test plan ties to acceptance test, and the acceptance test is supposed to test what's in the product spec. Going down, the software test tests against the software requirements, the integration test tests against the high-level design, and unit test tests against the detailed design. Now that's a lot of different testing, but each one is focusing on something different. So for example, integration test assumes the unit tests passed, therefore it assumes the detailed designs are correct, and it's really just interested in do the things play well together, not internal logic flaws. This way of looking at the development cycle emphasizes traceability and emphasizes saying, okay, well, you said you were going to do something. Did you really do it? The said you're going to do something is on the left side of the V. Did you really do it is on the right side. Peer reviews of all work products happen. So everything that is a work product and output, for example, software requirements or detailed design or source code, all those things are subject to peer review as an extra quality check. And so this way you have two ways of finding defects. You take a look and make sure the thing coming out of the box makes sense. And then later on in test, you go back and say, well, yeah, we created that thing. Does what we created actually match what's in the box? And by the time you're done at acceptance test, if you've done a good job, you're finding very few bugs in acceptance test. Let's spend a little time looking into what's inside the boxes of the V model we just saw. An important takeaway is when you say there's a design, that's not the code, it's an entirely different thing. The implementation is the code itself. And if there are comments in the code, that's not a design. That's a comment describing how the implementation works. A design is a completely different thing. There are two levels of design shown in this V. One is detailed design, DD, which is flowcharts, state charts, sketches of algorithms, control diagrams, things like this. So a detailed design is not how the code does the job. It's a very specific, detailed list of the types of things the code needs to do and the general idea of flow of control. High-level design, HLD, is the architecture and the component definitions. So it's the types of things in the system. It might be classes, it might be subsystems, it might be the general functions of the system, and a functional allocation to the pieces. So usually high-level design is boxes and arrows, and each box is a thing, and the arrows tell you how they relate to each other. It also typically includes network message definitions and interfaces to the outside world. Now, before you can do design and implementation, you need to know what you're building. The top left of the V deals with requirements. Generally, there are at least two levels of requirements in a V. One is the software requirements specification, or software requirements. That says what the software does, but not the how it does it. The idea of an SRS is that the software does everything in the SRS, but nothing that's outside it. It avoids details unless those details are absolutely mandatory to the marketing requirements, which we'll talk about in a second. And it's often paired with a hardware requirement spec. So if you have an SRS and a hardware requirement spec together, they tell the engineers what they're building at a very high level. Not how they're building it is the detailed design and below, but what they're building. Above the SRS is the product requirement spec. The PRS is the market-facing product requirements. Those are the things that you're actually selling to the customer. It's what the system does from a user point of view. And typically, it's the point of interface between, for example, marketing and the software development group. It might be a feature list. It might be a customer-specified acceptance test plan. It could be a lot of things, but the idea is the PRS says the customers want you to build this thing, and everything in there has to be a feature or a behavior. Whereas the SRS is at a lower level, and it says, okay, that's what they want. How exactly are we going to build that? That's the SRS. After you go PRS, SRS, then you do detailed design. Now you may say, that's a lot of paperwork. We have our product requirements, we have software requirements, we have a high-level design, we have a detailed design. What's up with having to do all that work instead of just writing the code? Well, there's a lesson that gets learned over and over again in engineering. And that lesson is, if you think good design is expensive, you should look at the cost of bad design. So here's a classic example. This is the Tacoma Narrows Bridge. And you can see that there was a problem with wind flutter that put the bridge deck into oscillations. And you can see just how crazy it is that this thing was oscillating that much with pavement and steel and everything else. And eventually, it resulted in a collapse of the bridge. Paying attention to the details of the design matters, both in bridges and in software. Now let's move on to the right side of the V, verification and validation. As you recall, the bottom of the V is implementation, which puts out the source code. What you do next is unit test. Unit test involves testing individual subroutines, procedures, modules, small chunks of code, and because it's a small chunk of code, it's possible to test it very thoroughly and make sure every statement, every branch gets executed and tested, which is something that's generally impractical to do at higher levels of integration. When you've thoroughly shaken down the modules, you move on to integration test. Now, because you've already covered all the code in the unit test, the point of integration test is not to do that again. Rather, integration test asks the question, do all the pieces work together? So unit test said, does each piece work? And integration test says, do the pieces in general work together as pairs and triples and clusters of modules? Integration test traces to the high-level design, which is also about do the pieces work together. Beyond that is software test. Software test traces to the software requirement spec. All right, we know the pieces work. We know they work together, but does it actually do what it's supposed to do? And that answers the question, did the engineers build the software they wanted to build? Beyond that is the acceptance test. That traces to the product requirement spec. So the software test is an engineering test. Does the software do what we wanted it to do? The acceptance test tells you whether the customers are happy with what it did. The engineers might have built something and it works perfectly, but it's not what the customers wanted. Or the customers might have a way of using it that the engineers didn't really think about. And so that's what the acceptance test is about, is making sure the customers will be happy with the output. Now, there's some other activities generally associated with V&V that aren't explicit boxes in the V. One is software quality assurance, which is, did you actually follow the steps? Did you follow the process? Or did you skip steps? Or do you have systematic quality problems? Another one is peer reviews, because every work product is supposed to get peer reviewed, so that's sort of implicit in all the arrows. And the last one you hear about is regression test. Regression test is a specific type of testing, typically at the system level, but can be used elsewhere, where you're looking to say, well, we fixed a bug. Did it stay fixed, or did it come back to life after we made another change? So regression testing is a particular type of testing technique used within the context of the V. It'll show up in the test boxes. Now, we've talked about all the boxes in the V, and each box puts out a work product, sometimes referred to as paper, because in the old days it really was a pile of paper. The question is, boy, that sounds like a lot of paper. How much paper do you really need? Well, there's an old military system development saying you should deploy when the paper is heavier than the system, including aircraft carriers. And trust me, those are pretty heavy. So the idea is with a heavyweight process, there is a lot of paper. But that might be what's required because the stakes are high, the systems are incredibly complicated. Sometimes that's really the only way to do it. Does this mean you need to be buried in paper? No. The point of having the paper is, first of all, to make sure you're actually doing methodical design and you have the ability to use the previous step. But also, it gives you a way to check the process health. If no piece of paper exists, then at least in my experience, it means you probably didn't do the step. You skipped a step. So you need the paper to check the process health. That's the SQA thing I was talking about a moment ago. But it's okay to be clever about minimizing the bulk and the type of paper. If the code has no paperwork, you should probably throw the code out because somebody just sat down and wrote the code and it's unlikely to have good quality. But that doesn't mean tons of paper if the job doesn't justify it. What you should do is put things on paper as you go through the V. So for example, if you have a whiteboard with some sticky notes on it and that's what you use to do the design, take a photo of the whiteboard with sticky notes. That counts. That documents that you did the sticky note part of the process. And if that's part of your process, you're good to go. You have a record of it. Make it a high resolution photo so if somebody needs to remember what's on the sticky note, they can go find it. And you're set. What you should avoid is documenting after writing the code. Sitting down, writing a pile of code, and then writing down the design after the fact is wasteful for two reasons. The first is the point of doing the design was to help you think about the code before you wrote it. And the second thing is probably when you have a bunch of code that wasn't done with the design and you create the design, it's going to be a very messy design and it'll be very painful to document it. So documentation is never what you should do. What you should do is create the work products as you're going and save them, not doing it after the fact. Another issue is people create a piece of paper, they use it in the next step, and then they never update it. So they do design, they create some code, they change the code, but they never redo the design. If you're going to change the code and not redo design, throw it away. There's no point keeping an out-of-date design. That'll just confuse everyone. Now that does not mean you should skip the design. What it means is once you have a design, if you change the code, you should go back and update the design. It's a fair point that if you're writing code that's going to be thrown away after 2 days of use, maybe there's no point maintaining the paper trail. Well, maybe. But most code that has any value lives much longer than you expect. And down the road, someone else is going to pay the price for that paper being missing or out of date. So if you need high-quality embedded software, then what you really should be doing is maintaining the paper that goes with the V throughout the life cycle of the software. Now that we've talked about each piece, let's go back and take a look at the big picture again. On a V, in the upper left, you specified a product, and so that's the product requirements. You then transfer to an engineering view of the system with the software and hardware requirements. You then create an architecture, so you break all those requirements up into a number of functions and a number of pieces and say, these are all the pieces we're going to build. You break it down into modules, so each piece is going to have a detailed design. So the architecture is a bunch of pieces. The designs are, what does each piece do? The implementation is the code to actually build each piece. And the unit test checks that the design is actually what the code does. The integration test tests that the architecture actually works the way you think it does. In other words, the units play well together. And the software test says, yeah, okay, everything plays well together, but does it actually do all the functions that are required by the product from an engineering point of view? And the acceptance test is a final check to say, yeah, users are going to like this product. While the V model is still heavily used, especially in the embedded system industry, there's a newer approach under the umbrella of Agile methods that attempts to solve the problem of what happens when requirements aren't known at the beginning of a project, or how do you deal with requirements that are likely to change without waiting around for all the requirements to be perfect before you start executing. There's a thing called the Agile Manifesto, which is worth a read. And a summary of some of the key values is it values individuals and interactions over processes and tools. It values working software over comprehensive documentation. It values customer collaboration over contract negotiation. And it values responding to change over following a plan. Now, these principles can be very helpful in certain situations, but it's important to note that these are relative statements. For example, working software over comprehensive documentation. That does not mean zero paper. What it means is the emphasis is on working software, and so on. An example Agile method approach is Scrum. In the Scrum process, there are daily stand-ups where people actually stand up to keep the meeting short, otherwise known as scrums. And that's a daily way for people to have face-to-face collaboration and communication to make sure things keep moving. Work is organized in generally 2 to 4 week long sprints, to incrementally add functionality. So instead of one big waterfall or even one big V, the way it works is for each 2 to 4 week long sprint, you take a few things that you want to build from the requirements backlog and you build them in a couple, 3 weeks, and then you demo at the end of the sprint. And theoretically, at the end of every sprint is a shippable product. So the idea is instead of building everything at once, you get something working, and over time, over each sprint, you add some more functions, and eventually it becomes a minimum viable product, something you can ship to a customer, and then over time you keep adding more functions. And the point of all this is that at every sprint you have the opportunity to notice that a requirement has changed or a new requirement has been added instead of having to go back and redo everything. Now the Scrum method, as well as most Agile methods, can be mapped to something like a V, but the terminology is different. For example, instead of requirements there are user stories, but in fact they perform a very similar function. Agile methods are not a free lunch. They come with their own challenges. Challenges I've seen in Agile approaches include if you have a geographically split team, especially in different time zones, it can make it difficult to do informal communications. This is typically resolved by having one team in each time zone or one team in each location and somehow coordinating across the teams. If there are external dependencies, such as another part of a system changes, this can also cause a problem because the idea is at the beginning of a Scrum, you take a snapshot of the system, you add some features, you're done at the end. But if other teams have also been making changes at the end, you have to deal with a reintegration problem of all the different changes that might not play nice with each other. By far, the biggest challenge with an Agile approach is that there's no time for extensive hardware-based testing at the end. There's a general presumption that all the tests are mostly automated or can be done in a very short amount of time. You only have 2 or 3 weeks, and that includes the testing. So they work best when you can automate or have very simple tests, but when tests involve setting up real hardware, loading in the software, and then running a bunch of physical tests on a piece of hardware, it can be a real challenge to fit that into a sprint. At this point, we're going to take a detour to watch a video, Introduction to Scrum, that takes about 7 minutes. After that video, the playlist will come back to more slides in this lecture. Here's a picture showing how a Scrum process might be organized. On the left, a product owner is creating a product backlog of user stories that form the product level requirements. A development team at the beginning of every sprint pulls some of the items out of the backlog and says, okay, these are the ones we're going to do on this sprint by doing sprint planning. Those selected user stories are put into the sprint backlog, and there's an iterative cycle where every day there's a daily Scrum that talks about what they're going to do this day. Items are pulled out of the sprint backlog, and over the course of the sprint are implemented, tested, and validated that they work. When the sprint is over, a potentially releasable increment is produced. And in principle, this is a product that could be shipped and is ready to go. In practice, sometimes it's only every second or third sprint that you actually get something you would want to ship. At the end of the sprint is a sprint review and a sprint retrospective. So again, what's happening is there is a list of product features which over time evolves. The development team pulls off a set of those user stories to be implemented in a particular sprint, and every day there's progress made. And at the end of the sprint, there's a product candidate that is potentially releasable put out. There's a retrospective, and then you go back and do the process again. So every 2 or 3 or 4 weeks, there's another sprint, and more progress is made on the product. As an exercise, ask yourself, how does this map to the V? Where are the requirements? Where's the design? Where's the test plan? Where's the acceptance test? In a viable Scrum process for high-quality software, all those things exist somewhere, just not necessarily as explicit boxes on this picture. While Agile approaches are often used in both enterprise and embedded software, sometimes they're a good fit and sometimes they're not. So it's useful to have a way to think about when they're a good fit and when maybe you need something a little bit different. Agile methods are at their best when there are small teams working on comparatively small code bases. That does not mean you can't do big things, but the sweet spot is a single small team with a small enough product that that team can handle the whole thing. It's good for everyday software quality, so the defect rate has to be moderately low, but it's not expected to be perfect. It can still provide value even if there's some small bugs. It's good for fast requirements change because every sprint you get a chance to do something different or do something new. It generally assumes highly skilled experts throughout the project and then includes during lifecycle maintenance. So there's a small, highly skilled team that knows exactly what to do, exactly how to do it, and they're there to design it, but they're also stay around to improve it and maintain it during the life cycle. And if everything's in their heads, that's okay because it's the same team working for the whole life cycle. An important management consideration is that Agile is at its best when developers can handle being empowered, usually meaning they're senior. The point of Agile is we have a bunch of developers, they know what to do, they know how to do it, get out of their way and let them do it. And if that describes your group, Agile can work well. In contrast, plan-driven, traditional, and so that means maybe waterfall and V, has a different sweet spot. It's at its best for large teams and large products. It's good for mission-critical products where every defect might possibly kill someone. So you don't say, well, we're pretty good, it's worth deploying, we'll fix the bugs later. No, you really have to get it right. So think about software that goes in airplanes for autopilots. It's good for stable requirements. So if you have fast changing requirements, plan-driven doesn't work as well. But if you know what your requirements are and they're not going to change much, plan-driven can be a lot more efficient. Plan-driven makes a conscious decision to put the high skill in the design phase, not in the detailed implementation phase. So what you assume is that as you're going down the V of the waterfall, the earlier stages have the highly skilled people making the right trade-offs and making good design choices. If you're going to make a big change, you need your top experts really looking at it carefully because if they make a bad decision, the cost gets amplified as you go down through the rest of the process. However, the trade-off is if you spend a lot of time in design and you have a rigorous process with enough paper to back it up, your developers do not have to all be senior. They don't have to all be able to be managers of themselves. So plan-driven works well if you have a lot of junior developers. That tends to correlate with large products. Let's face it, if you need 1,000 developers, it's going to be really hard to get 1,000 all senior people, all of them above average, to work on that project. You're going to have a mix of senior and junior, experienced, inexperienced. People are good at managing, people are not. And a plan-driven framework is going to be a lot easier to manage that kind of effort in. What about Agile methods used for embedded systems? It's not quite as obvious a fit. And so let's talk about some of the potential issues. A significant benefit of a well-run Agile project is that it can make good developers happier. Really capable developers don't like a lot of paperwork. They don't like a lot of interference. They'll just say, I know what I'm doing, go let me do my job. And Agile appeals to those kind of folks. Along with that, if you're in a situation where you know your requirements are going to change every few weeks, Agile is probably a better fit than Waterfall or V. But you still need to manage and moderate the risks, because if your requirements are changing every 3 weeks, you'll never actually get done. Agile might make the experience less painful, but you're still not going to get done until the requirements finish settling down. There are some issues and dysfunctions that happen with Agile commonly. I've seen all of these a number of times. So if you're going to use Agile, make sure you are aware of and mitigate the risks due to these issues. The first is Agile does not mean cowboy coding. If somebody says, oh, we're using Agile, what does that mean? It means we don't have to do paperwork anymore. No, that's not what Agile is. If it's, well, we don't have to follow a process because we're Agile. No, I just showed you a picture of an Agile process. So Agile doesn't mean do whatever you want. It means a different process model that you actually have to follow for this to work that has different trade-offs in a different organization. Undefined, undisciplined processes are bad news. And yes, Agile teams should follow a rigorously defined process. If there's an Agile team and you say, what process are you following? And they look at you and you say, draw it on the board. If they can't draw it on the board, they're not Agile. They're probably just going around doing stuff and claiming they're Agile. That usually ends poorly. Another issue is no paper Agile. If you have Agile that has gone all the way to zero paper at all, it might be okay for some applications, but basically you've decided that rather than write it down, all the information is going to be in the heads of a few people. If those people leave or retire or, as we like to say, win the lottery, you're going to have a problem because there's no record of the trade-offs that were made. Implicit knowledge can be efficient, especially with teams of 2 or 3 or 4 people, but it evaporates with the team and it does not scale well to really large teams. Can you do large projects with Agile? Well, I've seen it done, and usually it involves more paper for these kind of reasons. If you have a system that's 10 years old and was developed without any paperwork and you have to make changes or evolve it or build on it, it's an absolute nightmare. The no paper may help in the short term, but for a long-lived embedded system, there can be significant downstream costs. So be mindful of that when you decide how much paper to do. There's an issue that Agile more or less implicitly assumes 100% automated acceptance test, or at least a test that can be run in a couple days. Think about it. You've only got a 2-week or 3-week or 4-week sprint. That means you have to be able to run all the tests to make sure the system is working in a lot less than that, maybe only a day. If you have 100% automated tests and they run every night as part of your nightly build process, then you're probably in great shape. But if it takes 12 weeks of technicians pushing buttons and looking at outputs of an embedded system to do the product test, and you have a 3-week sprint, that doesn't work. There's no way to test in that environment fast enough to keep up with Agile. So that's an issue that has to be dealt with somehow. An underlying trade-off of Agile is it often implicitly assumes that defect escapes are low cost because the new version is only 2 to 4 weeks away. If you have a system where you can deploy updates in 24 hours or less, this might be viable. But if you're building embedded systems that once they're programmed, they go out to the field and it is difficult or impossible to update them, then the fact that the next sprint you fix the bug doesn't really help for all the products you shipped. That's a different trade-off than the primary sweet spot for an Agile process. Finally, an issue with Agile is it typically does not have independent process monitoring. It's rare to see an SQA, software quality assurance function. There are often embedded testers, and by embedded, that means embedded with the Agile team. So there may be a team that has some developers, some testers, and they work together and they all do the stand-ups together. But that's not quite the same as someone independently making sure the process is followed. Now, if you have senior responsible developers that are concentrating on doing the right thing, this might not be much of a problem, but not all teams are really seasoned developers that know how to follow a process with no one making sure that they didn't get it wrong or somehow skip a step by accident. SQA tells you if your process is working, and it's unusual to see that really called out in an Agile process. So you may be dysfunctional and have no idea there's a problem until you find out that your product doesn't work. Another way of looking at this is that many Agile teams trade off knowledge of how good their software is during development for a smaller team and faster progress. But at the end, either it worked out or it didn't, and so you're deferring knowing that. Wrapping up, let's take a look at best practices for software processes. First of all, you have to have a defined software process to be more than just slinging code around. That process has to include all the aspects shown in the V. So all the boxes in a V have to be done someplace. And in addition to that, some quality assurance function and some peer reviews. But it's okay to rename and reorganize the steps. All the steps have to get done, but it's okay to draw them in a circle. It's common to see Agile fall, some sort of hybrid, and that can be okay because the question is not, did you draw the picture to match a book, but rather, are all the pieces there and do they work together in a way that you need? It's also common to see bad processes or undefined processes dressed up with the latest buzzwords, and you should avoid that. Some pitfalls for software process, 2 big ones. The first is skipping steps to getting to testing faster means more bugs in test. And finding bugs in testing is more expensive. So you should avoid the failure mode of saying, oh yeah, we have to get this code written so we can get to test and start finding the bugs. What that really means is you're spending a lot of time writing really bad software with huge numbers of bugs in it, and it's going to take you even longer in test than you thought. If you're on a project where the way they're managing progress is by telling you you have to have the code all written by a certain date so that testing can get done, that's often a dysfunctional process. Another pitfall is using the wrong process because it's not a fit for what you're doing. If you have a 3-week or 3-month product life, that's an entirely different situation than a 30-year product life, and your process needs to reflect it, because don't forget, the process doesn't end when you ship the product. After you ship the product, you still have to fix bugs and deal with lifecycle support. The amount of formality in the process you execute when designing can support or undermine your ability to support the lifecycle after deployment.